In this work, we present POMP, a novel online method that can solve the active user search problem by learning optimal policy while exploring the environment. Different from state-of-the-art methods, POMP does not require a policy learning phase, but only needs a map of the environment, and information usually available or that can be easily extracted from a single exploration run. Let us consider an autonomous agent equipped with an RGB-D camera that has to navigate an indoor environment with the goal of approaching a specific target object. The agent should find the optimal path to the target object. For example, in the picture on the left, the black path must be avoided because it does not reach the target, while the green path should be preferred over the yellow one because it's a shorter path. While planning the trajectory, the robot must also explore the environment to find the object and estimate its position. On the right side, we have an example where the agent is asked to find a Red Bull can. The robot first rotates standing in the same position, and once the object is detected, it starts moving towards it. AVS is typically solved in two main ways, with deep learning or reinforcement learning. Both of these two approaches work in an offline manner, requiring training on a big amount of data to be effective. In practical use case, where training data is scarce or unavailable, these methods cannot be used. We propose POMP, an online method that can solve the AVS problem by learning optimal policy while exploring the environment. We assume that we have a priori model in the environment in form of a 2D grid map, like a floor map of the scene, from which we automatically generate the agent pose graph, which is the set of all the poses composed by location and orientation that the agent can reach. The method is then based on two main steps, OCP exploration and robust visual docking. During the exploration phase, the robot moves around the environment, maximizing the probability to observe the target object. Once the target object is detected, the agent will plan the shortest path to reach it by means of a Dijkstra algorithm. To be more robust, the object location will be updated after every move. The core of POMP is the exploration phase, which is performed with partially observable Markov decision process solved with a Monte-Carlo tree search algorithm. From the environmental map, we build a tree structured in the following way. The root node is the starting pose of the robot, intermediate nodes are the allowed robot poses, and leaves are the allowed object location. The tree levels are connected alternately by action and observation. The action is one of the possible moves that the agent can make from that pose, while the observation indicates whether the target object is visible from that location. We sample a high number of candidate object locations and then run simulation, letting the robot move randomly. A positive reward is assigned to every simulation that reaches a candidate location within a maximum number of moves. We then perform the action that accumulates the higher reward, or alternatively that leads to a positive reward more often. After the movement, the robot acquires a new observation. If the object is not present in the camera view, we can then prune the branch where the object was assumed to be visible from the current position. By doing so, we also remove from the candidate location pool the location only reachable from that specific branch. We repeat this procedure until the target object is located. We validate our method on the publicly available AVD dataset and we compare against it, a deep reinforcement learning method that is currently the state of the art for AVS. We use manual notation as output of the object detection module and we run over 500 searches for 3 houses of increasing difficulty level. As the evaluation metric, we use the success rate, which is the percentage of run where the robot has reached the object, in which a larger value indicates a more effective search. APL, which is the average path length of the successful runs. ASPPL, which is the average ratio between the shortest possible path and the length of the path output by the methods, in which a larger value indicates a higher absolute efficiency. We can clearly see that our method outperforms the random walk baseline and performs very close to the state of the art, even though we do not need to collect and annotate a massive amount of data for training. Additionally, we report the results of our method without the robust visual docking module. In this case, the success rate decreases as a consequence of erroneous estimation of object location. Additionally, we test how the success rate and path length change when the misdetection and false positive occur during detection. Interestingly, misdetection only affects the path length, while false positive only affects the success rate. This means that for tasks that require a high success rate, our method should be paired with a detector with high precision. If instead a shorter path length is desired, the detector should have a higher recall. Our method can then be tuned a priori to give a higher success rate or lower path length by choosing the appropriate detector. To recap, in this work we present POMP, an online motion planner for AVS with the following key characteristics. First, our method does not require a training step, so it can be applied even when there is no training data available. Secondly, our method is able to reach state-of-the-art performances comparable with training methods. And lastly, our method can be tuned a priori to reach different goals without the need of time-consuming hyperparameter optimization.